Okay, can you see my screen?
Yeah.
Okay, so this is the way Professor Shady presented his results, okay? In this case, as you can see here, this is, oh man, it doesn't mention the case, okay? But you have different type of, you have three of these curves or these figures, one for each one of the cases. Probably this is case 3, right? Yeah, multiple web case. So this is case 3. Okay, so what we do is, for example, let's suppose that we have the clamped case. Okay, let's suppose we have a clamped case under uniform load. Okay, so we have clamped case and uniform load. Okay, so we have something like this. This is our beam. And let's suppose we have something like this, right? So this is X, this is Y, and this is P sub 0, okay? I'm not going to do the details. You can do it later on. Okay, so immediately you see this, and what's the boundary conditions for this? On the left and on the right. Mr. Aizaga, are you there, Mr. Aizaga? Mr. Aizaga? No, Mr. Aizaga, what are the boundary conditions for this case? Mr. Aizaga? Mr. Chinchin, boundary conditions for this case?
The deflection is equal to 0 and the first derivative is equal to 0.
Exactly. So the slope, okay? So if we draw, we have to start here because there is no deflection, and we have to start by 0 for the slope. Similarly here, so we start at this point, and also we have to end horizontally because there is no rotation. So if we push downwards, we're going to have something like this, and we have to return and go back to this point. And we can see immediately that there are points here that the beam is sad. Here in the central part, the beam is happy, and on the right, the beam is sad again. So that means that more or less, on this region, the bending moment has to be negative, here has to be positive, and here has to be negative again because it's sad. So we're going to have something like this. Okay, so more or less, you can do the details to determine how much is each one of these spans, these distances. Okay, so if you want to calculate the effective breadth in this area, okay, this could be the C times L, which is this one here. Okay, now, in this area, or in this region, we're having trouble, right? Because we have a 0 here, and we end up here. So how do we calculate the CL for this area? Well, in that case, the recommendation is to take something like how can I say? It's like having an imaginary double of the beam. Okay, so eventually what we do is, if we want to calculate the effective breadth in this part, what we do is we take this here, there's a CL. So we can calculate a CL for this area and another for this one here. Okay, after we find this, we can calculate CL over B. Please, this is big B. Okay, in this case is the uniform load. Okay, and we could take a value, for example, like this, okay? So let's suppose that we go on, this is the plate, okay? And this is one element. There is another one here, another one here, but we're considered only from here to here. So this is B. Okay? Are you with me, people? Are you with me? Everybody with me? Miss Valdez, are you with me? Are you following me, Miss Valdez?
Yes, doctor.
Okay, because this is case 3. Okay, now we have found that the effective breadth is about 0.90 something in this case, right? So what we have to do is we have to calculate the inertia of this. But we know that the effective breadth is not 100%, it's 90 something. So what we have to do is like drawing a new section. Okay, let's do in. So up to here, this 100%. So I'm going to take this doesn't exist. This exists. Okay, and this from here to here, okay, is lambda over B times B. See, lambda over B is the percentage that you're taking here. So you don't take the full width. Why not? Because if you want to calculate the maximum stress, then you have to calculate only, you have to consider only a part of that. Okay, that means that you are going to have a higher normal stress than the value that is given to you by the beam theory. As you do this correction, you can calculate the inertia, I sub C. You know where the neutral axis is located, and you can proceed to calculate the stresses. Any questions about this procedure, people? Any questions about this procedure?
The little b is the flange down, or no?
No, the little b is half of large B. Let me go back. Here. You see the little b is that, so large B is that. You can see this also in the cases, in the case 3. Here. See, this is little b, okay? If you analyze the, from here until here, is large B. We have to be careful because this is one of the constants of integration. Did I answer your concern? Person who did the question?
Yes, doctor. Thank you.
Okay, okay, no problem, no problem. Okay, so that's the way we apply Shady's theory, okay? So we have to calculate the distribution of bending moment, then determine the distance between points of 0 bending moment, and with that we can enter one of these figures and calculate the effective. Usually the ratio lambda over B is what we call the effectiveness of the plate, okay? Lambda over B. Some people call it effectiveness of the flange. Okay? For example, you said that you can take, for example, 65% as effectiveness. That means that you take this B multiplied by 0.66, and that's the effective breadth of the flange. Okay, so it's a very typical way to call it. Now, this is Shady's theory. In these days, of course, that was a long time ago, but the classification societies, they have inherited a lot of these theories, and they, of course, they have improved because we have now the computer can help us. We can do many tests, and this is what we see. This is taken from the DNV. You can read it here. It says that this is in Rules for Ships. This is 2016, but you can find it easily. Part 3, Chapter 1, Section 3, Design Principles. Okay, and what is it what we have? Okay, here, instead of lambda, they call it B sub E here. Okay, we have to be careful, okay? And they say that that's equal to a constant times B. Okay? Now, how do we get C? And to get C, this is what they present, okay? They have a ratio A over B, and they have these constants, or these rows, each one of these for these values of R. Okay, now, let's see. What is A? A is the distance between points of zero bending moments. So that's equal basically to C times little c times L in Shady's work. See? CL is the distance between points of zero. And B, it says that it is the sum of plate winch on each side of girder. Okay? So it's basically this is our B. On each side of girder. Okay? And it says normally taken half the distance from the nearest girder or bulkhead. So he's telling us that if we have a plate and we have a girder here, and another girder here, another girder here, we're analyzing this one. And it's saying that on each side of the girder, it's taken half the distance. So the distance is from here to here. Half of that is here. From here to here, the half is that. So this is little b, but little b is for D and B. For us is large B. So we have to be careful. So B, A over B is equal to CL divided by large B. So this is DNV, and this is Shady work. Okay? And in this case, each one of these lines, it's for R, different number of point loads. Okay? And that's basically the number of stiffeners that you have. Okay? So let's suppose that we have, there is a figure, I couldn't include it because I had too much information. Okay, this is the reinforcement I want to analyze. But usually you have stiffeners in the other direction. Okay, so the number in this case is 1, 2, 3, 4. So in this case, I would use 4. If you have many of these, basically that's the case which was analyzed by Shady. Shady analyzed a very large case, okay? But as you reduce the number of stiffeners, you could expect some difference, okay? And that's what you see in this direction, okay? So if you want to compare this with this, what you have to do is you can take this line okay, because we have, for this case, we have a very large number of stiffeners, are large, 6 or larger, and let's take each one of these values. For example, why don't we take this value? For 3, a value of 3, we have 0.84. Let's go back. For 3, In this case, it's about 0.9. So it's similar, but not quite the same. Okay. So it's questions about this, people? Any questions about this?
Doctor, here is
Yep.
the number of stiffeners.
Yeah.
Yeah. Okay.
Yeah. So in this figure, okay, you have another girder. Let's suppose the other girder is about here. Okay. So from here to here, this is B over 2. On the other side, you have also B. And in the other direction, you have the little stiffeners. Okay, now let's now go to the case in your for your report. Okay, you have something like this in your in the experiment, right? And you have, I think you had only three strain gauges because we have problems with one of them, right? Okay, so let's suppose, I don't remember then, we had three. I think we had one about here, another in the center, and the other was about 1/4, right? Do you remember the numbers of this? Anybody remembers the numbers of this?
One, two, three. The
Which-
of
Engage.
the,
This one here was what? Number what?
is 3.
That's 3. In the center was 2. And on the side was 1. You have to check this. I'm not sure. Okay, now, what do we have to do? So we can plot this, okay? In this direction, we have epsilon sub j, because we have 3 values. And we can multiply that by E. If I multiply this by E, what I am going to obtain, Mr. Vanegas? What do I obtain if I multiply these two? Vanegas? Mr. Vanegas? No? Mr. Vanegas, come
The
on.
stress.
Exactly. You get the stress. So it's you see that we're getting close to what a shady did. Okay, so from here to here, this is minus B and this is plus B. So from here to here is the same as here to here. Okay, now this epsilon 1 is very close to this point. It's not exactly on the edge. So we have to be careful. Let's suppose that I have a value here. Okay, let me put it positive, even though it is, well, let's change sign. Okay, so it's going to have positive value. In the central part, probably it's going to be larger than that. And on the other side, it's probably we're going to have something like this. What we can do is we can complete this like this. Okay, now, this is the only information that we have for a certain value of the force. Okay, if you know the value of the force that you're applying, you can calculate the moment. Okay, and we can proceed in all of that. Now, what do next? What do we do next? Well, what we have to do is complete this information. Okay, we're going to assume that this is symmetric. So, and on this side here, we assume it is symmetric. So we don't know these two values. What we assume that they're symmetric. And now, well, now we can do is try to make it an approximation. There. So you have 5 points, and with these 5 points, you know it is symmetric. You can determine the distribution of the normal stress. Now, what's next? Ms. Sanchez, how do you calculate the effective breadth in this case? Ms. Sanchez.
I'm here, doctor. The effective breadth.
How would you calculate it?
With the values that normal stress.
It's kind of difficult, right? I know. It's, I'm sorry, I put you in trouble. Let's see. Let's recall, okay? Lambda is the integration from 0 to b of what? Sigma x as function of y dy. And we have to divide it by, anybody? Divided by what?
Maximum stress.
So in this case, this is the maximum value. So this is the maximum value. So what we have to do is to integrate. So integrate from here until here. So we have to integrate this area. Can you integrate that? Well, what you have to do is you have to develop an interpolation. So you complete this curve here, you have to do it. And once you have that, you can integrate this, you can follow, for example, remember the rules to integrate numerically, anybody? Rules to integrate numerically? Rules for integration, people?
Simpson, doctor.
Exactly.
Simpson.
Simpson rule, exactly, Simpson rule. If you use only, notice that I don't, see, I was playing around with the results yesterday. If I have something like this, okay, you see that this has one curvature open in that direction. But here you have the maximum. So you have probably a curvature looking downwards. So if you use only 3 points for integration, 1 for 1, if you use the first Simpson rule, I don't think it's going to give you a good result. So you have to use the next partition, which is 5. So you go 1, 4, 2, 4, 1. Okay. So you have to do is take this value, this, and that, and integrate using first Simpson rule. So you have to do the interpolation, evaluate that in these 4 points, and then do the integration. After you do the integration, you do this lambda. People, any questions?
Doctor, I have a question.
Yeah.
For example, in our case, in the experiment, we have a lot of points, but we want to establish only, for example, one load.
Yes. Let me go there. Okay, now that's my question. See, right now is okay. We're talking about experimental results right now. Okay, now your question is, okay, I have a value for the time, and then you have epsilon 1, epsilon 2, epsilon 3, right? Okay, now, what you can do, there are several things that you can do. Okay, with these values, you can interpolate and you can get the values of this curve. So that probably is going to be a cubic curve, right? So you can have A0, A1, A2, and A3. Okay. After you do this, you can do this for every point. That's Excel. Excel is so easy. Then you can evaluate here, 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 and all of that. So it's going to get sigma 1, 2, and sigma 5. And then you this is what we're doing. We're doing an interpolation. You can do all other options, right? This is what I would like to see, but let's see what you can do. Okay, now you have for every point for every time, you have these three values. With these three values, you can do an interpolation, remembering that here, the slope has to be 0. With these 4 values, you can evaluate at the points where you want. Okay, so you evaluate here, and you evaluate here, 2, 3, and 4. So 0, 1. Yeah. So you have this value here. And after you this, you don't need this. You don't need this really, because if you have this 8, 1, 2, 3, 4, you can integrate, right? So this is an approximation. It's approximated by this polynomial. So you don't need to evaluate this. You can calculate lambda. Since you are dividing both by and multiplying both numerator and denominator by E to get the stress, you know that it's going to cancel. So you need to consider stresses. You can go on and calculate everything with strengths. This is what we obtain, lambda. And this is experimental. Okay, so it's a good idea if you take values, for example, about here, and you plot this function. So here you plot this distribution. It's a good idea for you to see how they look like. Okay, it's a good idea. So you can present these results, the distribution, and also you can present a value of lambda, which is supposed to be constant. It's not. It's going to be a mess, but let's see what we obtain. Okay. Any questions about this? This is just with the experimental results. Any questions? No. No questions. Oh, okay. Now, let me open a new page. Now, how about the theoretical part? Okay, because the idea is always to compare. Now, in this case, you have, this is the most interesting part. Okay, this is F, and the shear force, or the bending moment, because that's what is interesting for us, is something like what? It's a concentrated, so the shear force is going to be like this. So it's going to be positive like this. more or
Doctor,
less.
you are not sharing any screen.
I know. Oh, shoot. Then say that. Now, you see it now?
Yeah, you're good.
Yes, doctor.
Okay, so this is the case you are going to analyze, one of the two cases, okay? So you have a concentrated force in the central part, and then this more or less is going to be this, what did I do? Anyway. Okay. Okay, so this is distribution of bending moment. So this is L, this is L over 2, this is L over 2. Question, how much is going to be CL? To calculate the bending moment, to calculate the effect. How much is going to be CL? C times L.
Just L.
Exactly. Just L, exactly. So the effective is going to be very high. Oh, Jesus Christ. Come on. So this is going to be L directly. Jesus. Okay. Now, remember, this is the distance between the points of support, not the total length of the beam. Okay, you have to be careful because the beam was a little bit longer than that. But we need only from here to here. That's all what we need. Now, about here, more or less, let's call it X1. That's the position where you have the strain gauges. Okay, now, B is data. So you have CL over B. Okay. This is known. So what you can do is you can go to, let me go back here. You can go to DNV rules, okay? Get this table. And according to the ratio A over B, what you have, you can take its value of C for R less than 3, because there are no, in this case, there was no stiffeners, and evaluate BE over B. Okay, so CL in this case is L, because this is the distribution of bending moment. B is the width, So from here to here, I'm sorry, from here to here, you have this information because you measure the width from here to here, that's B. Let's consider a small number of reinforcements because there was no reinforcements. Okay, so you enter in the table and get a value of C. With C, you multiply by B, or directly the C is going to be the ratio. Any questions? Questions? Okay.
Could you explain why R is equal to 3?
In this case, there were no stiffeners because you have a concentrated force and there was nothing in between. So that's why we consider that R is less than 3 in this case. What happens with the next case, the other case? I don't know, how do you call it, case 1 or 2? So we have F over 2 and F over 2. This distance was A, right? Symmetric. Now, in this case, we have about here, in X1, we had the strain gauges. This is the same as this one. What happens now? Well, in this case, the shear force, it was like this. And like this. So this is F over 2, negative. So in this area, we are free from shear effects. What happens if there are no shear stresses? That means that there is no difference between pure bending moment, pure bending theory. So in the second case, basically, we expect to have a more uniform distribution of normal stresses. That's what we expect. Okay, so theoretically, in this case, okay, if this is the section, okay, this is X. Theoretically, we expect the normal stress distribution to be like this. Compressive, but uniform. So it's going to be minus mz y over I sub c. So in this case, the values of the strains should be close. Remember, this is experimental, so we can never expect to follow exactly the theory. So it's going to be close. That's enough. So that's going to be a good way to check these results. What happens in reality? What happened was that what I was trying, we were trying to set up this experiment the best way we can, but we had some problems with the beam. See, we were trying to apply the force in the central line. But it was possible that there was some deformation. So it was likely that there was some torsion involved in the problem. Okay, that means that the distribution of this stress would be, we have to expect it to be a little bit different than the one that we calculated. Remember that when you sat the beam, there was some shaking, some motion, and you have to put something behind in order to try to keep it steady. That means that there was not completely horizontal. So when you apply a force, and this is not completely horizontal, it would torque, it would twist a little bit, and then it start bending. So it was a combination of mainly bending, but some included some torsion. And that would take our results away from exactly the way we expected them to be. Okay, so we have to be patient with these results, but that's what we need to calculate. So we have experimental, and we have to compare it with theoretical results. Questions, please, questions. No questions, everything is very well understood. Mr. Romero, who is in your group?
Number 8.
Who are your teammates?
Ronald Villalba, Palma María José,
Okay, so that's
Chiriboga.
okay, so that's 4. And you have talked about this? Have you talked about this report?
Yesterday, I haven't the one Zoom Teams
Okay,
for the review the homework.
okay. Who is the leader of this group? The responsible person for this group?
The leader is Palma Jimenez.
So there always has to be a leader. And then what we can do is we can change for the second experiment. So it's like the person responsible, right? So you have to set up Miss Palma. Are you there? No, Miss Jimenez, are you there? Miss Jimenez? Right, you said Miss Jimenez Palma, right? Or am I wrong? Are you there?
Doctor, I have a question.
Yeah, go on.
In the first case, we put the strain gauge at the quarter of the length of the beam, and in the case 2, in the middle of the beam, always or not exactly?
Oh man. Not exactly. That's the reason why in the that's I'm talking about right now. I'm talking about the calculation of the of effective breadth. Okay, are you talking about the second part of the? Let me. Can you see my screen?
Yes, sir.
Okay. For the second part, and I'm looking from the side. So these are the 2 flanges, and this is the web. This is X, and this is Y. Okay, this is the height. There. Okay, now, in here, you are supposed to have the 3 strain gauges, right? So I have one here, the other here, and the other here. I think this was S1, S2, and S3. I'm not sure about that. So this is at 0 degrees. This is at 45 degrees. This is at 60 degrees. No, I'm sorry, 90 degrees. And with these values, you are supposed to calculate gamma XY. Now, as you can see here, there is some difference between this, the center of the gauge is here, and the center of the gauge is here. So there is some vertical difference between this point and this point here. So they were supposed to be at the same position, but yeah, there is some difference. But we can assume that they are more or less in one single position. So they are measuring, the 3 are measuring the strains in the 3 directions, but at the same position. We have to assume that's all what I can say. So if we use a larger section, the error because of this difference will be smaller. But the problem with that is we will have to apply a larger force, and I don't want to do that. So yes, we have to assume that they are in the same position. Is this what you were worried about, Ms. Valdez? Or I misunderstood your question. Ms. Valdez?
Yes, doctor.
Okay. So you have to review in solid mechanics book about how to calculate using the strain, the distribution of strain in a certain point from what's the name? What's the name of these 3 disposition, 3 gauges? Isaac, help me out. How do you call it? This combination of 3 gauges.
It's in rosette.
It's a rosette.
Rosette.
Doctor,
Okay.
I have a question.
Just a second, please. Miss Valdez. Okay, so this is what you have to review. You have to review in the solid mechanics book how you get a rosette of gauges. Okay, so they explain to you very simple way. If you have these 3 values, how do you calculate the gamma? And from that point, you can go on.
Okay, doctor.
And, okay, with gamma, you calculate tau. And this is experimental, and you compare it with the value from our formula. Okay, so those are 2 parts of the report. Yes, somebody was going to ask me something. Go on.
It's about the Q value in the formula. From where to where we have to take the.
You tell me. You tell me. Here I have the section, and we are considering the position, this position. So this is the cut.
Where are you writing? I can see where you wrote in the screen. I don't know if
there's something with my, is there any problem with my, can you see my screen?
Yes, but I didn't notice if you wrote something in the screen.
Let me change color. Here. Let me draw this, okay? See, right now, how can I do it? Something like this. So this is the web, okay? This is the web. This is the web, like this, okay? This is X direction, Y direction. Up here, in the top, we have the flange. Now, if I measure epsilon in z direction, that means that I'm measuring this, how this elongates. Okay, this is what I'm measuring here. If I put a strain gauge in this direction. Okay, now, similar in the vertical and similar at 45 degrees. Okay, so if I use this in order to calculate gamma, okay, what I'm going to obtain is the distortion of this element. So what I'm going to obtain is, this is the original. And what I'm going to obtain is this. See this angle here and this angle here. The summation of those two, I'm going to give you gamma xy. So if I make a cut here, okay, that's your cut. You have to integrate from here. This is the sector that you're going to consider. What happened if I end here? Mr. Ortega, what happens if I end here? I integrate from here to here. That's easy, a rectangle, right? What happened here? Would you stop here, Mr. Ortega?
Well, for calculate the shear force, we can only consider the vertical elements.
But the problem is that you want to calculate the shear stress here, and the shear stress here is 0?
Yes, doctor.
No. So you have to go up all the way up to here. And here, this is 0. And in this cut, because this is the section that you are considering, in this cut is 0? No. So you have to go up to here. So down here, tau is 0. Here, tau is 0. And in here, you calculate tau, and this is what you want to calculate, right? Because that is related to gamma xy. So you have to start here and integrate all the way up to here and up to here. And in this case, on this section, you have a DFS, and this is equal to Q dx, and go all the way. And for this DFS, you include the integration of the first moment of this cross area. I don't know the name of the person who was asking the question. Did I answer your concern?
Yes.
And your name is?
Esau Hidrobo.
Okay, nice to meet you. Did I answer your concern, Mr. Hidrobo?
Yes.
Okay, good. Anybody else, please? Anybody else? No? Okay, people. I wanted to have a couple of seconds. Can you give me 5 minutes? 5 minutes in order to say a couple of words about the quiz. I don't know that you don't want to talk about it, but we have to. At the beginning of a session of the quiz, I remind you that the first thing that you have to do was what? Please everybody turn on your cameras. Okay, it's turn on your cameras. I have the impression that they just make the connection and leave to do anything. So I want to see if you're there, really. Okay. The first thing that I said to you, I remind you, was what? Does anybody remember? What was the first thing that you have to do when you when you take a test?
Read.
Read. And in the text, for example, in problem 1, it says that you can neglect the weight of the hull, right? And some of you included the weight of the hull. That means that you did not read. So you did not read the question and start doing, I don't know what. So if you don't read, how can you know what they are asking from you? But when you become engineers, okay, a big problem is that you have to talk to a ship owner. And the ship owner, most of the time, is not an engineer. Not an engineer. It's not an engineer. It's a lawyer, it's a businessman or something like that. So the language, the way they think, they're different. So the first thing that you have to do is, in this case, is read. In that case, understand what he needs or she needs. If you do not understand what he or she needs, what are you going to design? Another thing that I found is that, let me share. These are the results, okay? The statistics. Some people write something like this. I don't know if I can write now. I cannot write here. You can write something like this. Okay, you say at x equal to equal to 0, you say the shear force is equal to 0. That's incorrect, because you are saying that this is a function. If you take one value of this function, you have to write v at x equals 0, it's whatever value. This is an algebraic expression. This is a function. So you have millions. This is a continuous function. Another thing that you forget about the EI, for example, you said v comma xx equal to minus m0. This has units of force times length. This has units of 1 over length. They can't be equal. We said this in class. So you're missing here the EI sub c. Another thing that worries me is that you have to consider the section beam. This is the baseline. Here you measure y prime. Do you need to do a calculation in order to determine where the centroid of this section is? Do you need that? Mr. Aizaga, do you know where the centroid of this is?
Yes, doctor.
I know too. It's here. So this is 100. The problem is that, please review your work. Review your work. and see how many of you calculated something different than 100 and said nothing. So you said, I calculated, I don't know, 70 something millimeters, and you went on with the calculation. That means that you're not thinking. This is a symmetric section. If you obtain a value which is different than 100, you shouldn't go on. You should go back and check what is the error. Okay, we're late, and there are a couple of more things that I wanted to tell you about this evaluation. I'm trying to prepare a poll about maybe 4 or 5 questions I would like you to answer, because I would like to see what's in your mind, okay? What can I do from my side in order to improve, okay? But I would like to see what you have in your mind, okay? So I'm going to prepare a very short, very small poll, and I would like to give it to you, okay? So please try to answer before Thursday's session, okay? So on Thursday, at least I will try to absorb what you have in your mind, and I'll try to see if I can do any changes in order to improve our results, okay? I'll be available tonight at 8 p.m. or starting at 8 p.m. if you have any questions about the evaluation. I'll try to listen to you one at a time, because somebody could ask me something which is kind of not personal, but at least these things about evaluation has to be treated like that, right? Everybody has the right to be treated individually as far as this is concerned. So in the way you come to the waiting room in the same order, I will get to you in the session, and I will try to answer as much as I can. Please remember that I have all night, so I'll give 10 minutes to each one of you. Okay, so if you want to talk, comment, any other thing that you want to say something right now?
Doctor, sorry, I forgot to ask you about what is going to be the format to present the report in the laboratory, because they only posted the instructions, but no.
Yeah, only 5 pages, but I'm going to, Isaac, do you have the, oh man, I think Isaac left because he had a class. Okay, I'll do it right away. I'll post a format. It's a common format for technical articles in engineering, so you can follow that. It has 2 columns, and you have to follow the format. Yes, the size, the size of the letters, titles, and all of that. The way they present the names of the figures, the tables. See, the name of the figures is below the figure. The number of the table is above the table, and things like that. Yeah, thank you very much. And also the way they call it the references. You don't need to use zillions of references. Maybe 2 or 3, that's enough. That's enough. I mean, you don't need to fill this with 10 references that you didn't review. Okay, thank you very much for that reminder.
Doctor,
yeah, go on.
Excuse me, that I have a problem that resolution because the question 2, 1 page is missing. The second part of the resolution is not here.
Let me review. Let me get you are.
Thank you.
Promise. I'll review it. Let me. You said page 2, right?
Question 2, page 2.
Okay, I'll review it right away because I have it here in my office.
Thank you, thank you.
No problem,
Doctor.
no problem, no problem.
Doctor, if we include annexes in our report, that counts as pages, and we cannot accept the 5 pages.
Yes, yes. In a couple of years, you will be publishing something, some of your work, and you will see that, for example, you want to participate in a congress, in a technical congress, and you present a work, a paper, and they tell you, for example, we accept 8 pages, and this is the format. And you said, but yeah, but the appendix is no, 8 pages, no, 8 pages. So you have to break your head thinking about how to summarize this. Yes, that's, so you have to start worrying about that. Also, when you present, for example, you present a proposal, right, to somebody, and you present what, 100 pages? They don't have the time to read it. So what do you have to do? You have to present something in a very concise, precise way. And all the basic information has to be there. When I see something like 5 pages, yes, I can read it. But you give me 20, man, you just see the 20 pages is a lot. So yeah, you have to do a good effort in trying to summarize. So try to think in terms of what do I really need for this? If I don't need it, don't include it. In Spanish, the word is lata. Right? So you don't need the lata because I don't have to read it because that's engineering SAC work. But he's trying to complete his thesis, his master thesis. And you put him to read 20 pages? That's not fair. That's why I say 5 pages and that's all. 5 pages, everything has to be in there.
Okay.
Okay, that's the reason. That's the reason why I do it. Any other questions? General questions? Okay, if not, then I'll be available to you tonight at 8 p.m. Okay, bye now.
Thank you, Doctor.
You're welcome.